you have a transformation from the time domain. So instead of having a time as a variable and a differential equation, I can have an alternative system of linear equations with complex variables, and these are easier to deal with. And then once I'm done with the analysis, once I'm done solving this system, let's say, I can use the inverse Laplace transform to go back to the time domain. So let's talk about some properties. So the first property we want to say is that a system is linear if it satisfies two properties. There is what's called this principle of superposition, meaning that if I have an excitation of two inputs, the result is really you just add the outcome of them. So this means that if I have a system and I give it U1 and it gives me Y1, okay, this is separate from Y2 and U2. Similarly, if I do the system and give it U2 and it also gives me Y2, then what happens is if I apply the summation of Y1 plus Y2, U1 plus U2, it gives me Y1 plus Y2, meaning it will act as if it will just add the two separate outputs. So if I give it an input here, that is U1 plus U2, it will simply give me Y1 plus Y2. This is the superposition. If I have multiple inputs, I can easily set let's say, set one input to be positive and the others to be zero, analyze its effect, and then do the same analysis for the other inputs, and then I can just add everything together, and that will give me the output of the system. If I can't have this property, then what happens is that I cannot separate the inputs because there is a higher correlation between them, and that can complicate the analysis. There is also what's called the principle of homogeneity. So basically, if I scale the input by a number, the output is scaled the same way. So if I have U1 again, and I have a system here, and it gives me Y1, then if I just scale the input by a number, call it A, then that scalar will just propagate to the output as is. Now, if we combine the two, we can have the following. We say that a function is linear if it satisfies the following property. For example, if A1, the function, as a function of A1 U1 plus A2 U2, this is equal to what? A1 f of U1 plus A2 f of U2. This is a check, or let's say this is one way of checking linearity by a simple test. You just assume two inputs, U1 and U2, and you have two scalars, A1 and A2. If the result gives you, if you substitute this entire thing, and it gives you A1 f of U1 plus A2 f of U2, then the function is linear, or the system is linear. Now, if I apply this to any linear function, then then this is one way to check the operator f. Now, what if f of x is x cubed, nonlinear, right? And if you pass it to this test, obviously you will not get this result, because you will get a1 cube u1 cube plus a2 cube u2 cube. right? Similarly, if f of x is just x, which is a linear function, then you will see that it will pass this test. Why? Because if you plug this argument into it, you will have a1 u1 plus a2 u2, and u1 is simply f of u1, right? According to this function. So you're done. Even if you add any scalar here, it will not affect the result. So this is how you can check if the function is linear or not, or if the system is linear or not. Of course, I mean with system, and you can have this definition is really generalizable to beyond just single valued functions. Any questions so far? All right, so we can have two examples. You'll see that this will have these properties. This will not have these properties because it's nonlinear, and this will have them. So either you can try them separately, superposition or homogeneity, or you can try what I just showed you, that simple test, a1 e1 plus a2 e2. Eventually, you'll get the same thing. All right, now let's go to complex numbers. So we say that a complex number has this form, x plus jy, where j is root minus 1. X is the real part of z, a complex number, and y is the imaginary part. We denote it by rez and also imz. And we will largely work with complex variables and complex numbers for most of the remaining part of this course. By the way, if you go to the reading assignment, the Appendix G will give you a review of complex numbers, and handout 3 is the reference for this topic. After this topic, we will go to the textbook. We will start using it. But for now, the handouts will be the main source for these topics. Because not everything we want to cover in this course is actually available in the textbook that we have. Okay. So now we say that two complex numbers, z1 and z2, are equal if and only if both real and imaginary parts are equal. We cannot say these are equal unless x1 is equal to x2 and y1 is equal to y2. If you have just x1 equal to x2 and this is not equal, y1 is equal to y2, then this is not equivalent. Okay? We can have a rectangular representation of any complex number. So where the vertical axis is the imaginary axis and the real axis is the horizontal axis. So with this, if I have S1 as a complex number, it's equal to x plus jy, where x corresponds to the real axis and y corresponds to imaginary axis. And we will use these kind of representations a lot in this course. This is called the complex plane or the S-plane. Typically, we use S to represent complex variables and T to represent the time domain variable. So in a sense, after you do the Laplace transform, instead of having a system, let me call it capital F, which has a lot of functions, or let's say a couple of functions that are functions of time, we go to another system, call it H, which has a function, which is like a set of functions that are complex valued, where S is the imaginary variable. So in a sense, what you do here with the Laplace transform is that instead of working with time, and it's complicated due to the differential equations, I can go to another set of functions that are in which S is the variable instead of T, and these functions are easier to deal with. So I do my analysis here Once I'm done, I go back to I do the inverse Laplace transform, and I go back to the time domain with a good solution. The reason we do this is that it's easier to do it this way rather than working with ordinary differential equations. Any questions so far? Okay. Let me see if somebody typed anything. Now we have the polar representation. So for the same x and y, for the same s variable, this is a vector, right? So it has a magnitude and it has an angle. So basically, I can represent this in polar form, where rho is the magnitude, and the angle here, theta, is the angle from the real axis up to that line. So, by the way, everything in this course we use radians. We do not use degrees. So everything is in radians. And sometimes it's easier to work with polar forms than rectangular representation. But both are equivalent. So to have an example of convergence, so I have 3 here plus 4j. So what is the magnitude? It's basically root 9 plus 16, which is equal to 5. What is the angle? The angle, it's tan inverse of the imaginary part over the real part. So this 0.9 is really tan inverse of 4. Why is it 4? Because it's this guy over 3. Why is it 3? Because it's this guy, the horizontal axis. You take that 4 and you have this 3, and you get a certain angle. That's the theta that we're looking for. We have what's called Euler formula. This is a very powerful formula, and it has a lot of applications in control, signal processing, a lot of domains. So what it says is that e to the power of j theta is equal to cosine theta plus j sine theta. Later on, we will keep using it. We will use it a lot. But typically for now, let's just take it as is, and we will see why it's very important. So if we do that, 5e to the power of j 0.9 is simply just 5 cosine that angle, 0.9273, plus j, 5 sine that same angle. Any questions so far?
Clear, doctor.
All right. So then we have addition, subtraction. This is very simple. So you add the real parts together or subtract the real parts and then add or subtract the imaginary parts. Now, if I have two complex numbers minus, let's say, just a real number, then this is just, this will affect only the real part and it has no imaginary part. So how about multiplication and division? Any idea? Okay, so for multiplication, again, you can either work with the rectangular form or the polar form. I mean, the polar is really easier when it comes to multiplication and division. And let's have an example. So if I want to multiply z1 by z2, then what happens is that I have x1, x2, then plus j x1 plus x1 y2 plus y1 x2 plus j squared y1 y2. This is simply minus 1. So essentially, we'll have just minus that. On polar form, this is just r1, r2, e to the power of j, theta 1 plus theta 2. Now, if I do the division of z1 over z2, then it really gets messy with the rectangular form. But if I apply the polar form, I just have, I just have r1 over r2 e to the power of j, theta 1 minus theta 2, right? Now let me remove this and show it to you formally. Again, it's similar to what we had. With the division, you see that the rectangular form is really a bit hectic, but with the polar form, it's easier to deal with. So it really depends on what you want to do. All right. We have small examples here for you to play with. I will not go through it because it's easy. But once you study this material, you might just do a small practice. For example, if you look at this one, the last one, under the red line, if I have 2 root 2 e to the power j pi over 4, then root 2 e to the power minus j pi over 4, then essentially what we get is just 4, because this will be 0. Then we have the conjugate. So if I have x plus jy, then x minus jy is the conjugate of it. And if we plot these in the S-plane or the complex plane, then you will have a vertical line between the two. You'll have one above the real axis and one below the real axis. Now, conjugates, by definition, they will have the same magnitude. So they'll have the same real part, but a different imaginary part, again, because of the plus and minus signs. Also, can imagine, because the real parts are identical, then s plus s bar, the real parts of them, over 2 is simply x, and y is the difference between the 2 over 2j. I mean, these are simple properties that you all know of. So again, this is just a refresher. So we will now move to the main concept. But there are some terminologies or keywords that we know. For example, the conjugate, the modulus or the magnitude, the real part, imaginary part, polar coordinates, complex plane, imaginary axis, pure imaginary. If you don't know any of these words, please let me know so I can explain it. Otherwise, I will assume that you know it. Yes, Faisal.
Doctor, can you explain again, sorry, the conjugate?
Okay, so any complex number has a conjugate, right? So if you have x plus jy, its conjugate is x minus jy. So basically you flip the sign for the imaginary part. That's it. And if you show this in the complex plane, then if I have s here, then its conjugate will be just vertical to it. You'll have a vertical line until you hit the conjugate. That's pretty much it. And they have the same magnitude. Because if you apply the magnitude formula, you will see that they have the same magnitude. And that's pretty much it. Is it clear? Good. Okay. All right. So now we're ready to introduce the Laplace transform. So why do we need the Laplace transform? Any ideas? I've already mentioned it earlier today, so maybe now you tell me why we need it.
To solve a system of equations that are hard to solve otherwise.
To solve a system of equations that is hard to solve otherwise. Are you Mazen? Because I saw Mazen raising his hand.
Mohammed Nasser.
Mohammed Nasser. Okay. Yes, Mazen. Thank you, Mohammed.
To solve ordinary differential equation easily.
Okay, to solve ordinary differential equation easy. So when you worked with the mechanical and electrical systems, you had ODEs, and these ODEs, to solve them, things might get complicated. So we need something that is easier to deal with, something that we can deal with at the level of math 001. Okay, what is the Laplace transform? It's a transform of the ODE into, let's say, a set of linear equations. Also, there are some questions that we need to answer, is that sometimes it does not exist, sometimes it exists, dependent on the properties of the system. So we will cover that, inshallah, in this unit. So just to give you an idea, if I have this differential equation, x dot plus 2x equal to 0, where the initial condition is 1, then the solution is this guy, okay? But maybe for this one it's obvious, but it's not always obvious to go from this side to this side. So with the Laplace transform, look what happens. Now, if I tell you the Laplace transform and what it is, you will easily, from the first instinct, from the first look at it, you will be able to give me this equation. And then by simple manipulations, you will get this equation. And you will see that using the inverse Laplace transform immediately, if I give you this fraction, you will know that x of t is just this guy. So it's easy to deal with these kind of algebraic equations than dealing with differential equations. And that's why we need the Laplace transform, and this is how we use it. We go from the differential equation to an algebraic equation, and then we do some analysis over here, some control design. Once we're done, we have something looks like this. For example, 1 over s plus 2, or whatever that you have. Then using inverse Laplace transform, you get the solution. And there you go. The solution will tell you the behavior of the system as t varies. So for example, here x of t tells you what is the output of x. This can be a displacement, a velocity, whatever you want it to be, as time varies from 0 to infinity. In this case, it will look like this, something like this. Because when t goes to infinity, this will go to 0. When t is 0, this is, and then it will decay. Something like that. So, some distinctions. If I have a function here, then I use the Laplace transform. So you see, I have a function of time. Now using the Laplace transform, it's a function of s, where s is a complex variable. So we go from a real variable to a complex variable, and then we go from a real function to a complex valued function. Now, if we do the inverse Laplace transform, we go back to the original function. Any questions? Okay. So we have time domain, which is real valued, and frequency domain. We call it frequency domain, this one. So let's recall a fact from calculus. If you integrate a function of two variables with respect to one of them, then the result is a function of the second variable. So let's clarify. So suppose I have a function f of x and y. We have two variables, right? If I integrate with respect to y only, let's say, then the result will be a function, another function, call it g of x. The reason is that once you do the integral, you basically evaluate all possible values of y and do that operation, all of them, you cover all of them. So in the end, you get a function of just x. It's not the same as f, but it is some function. This is a fact from calculus. Now, we can use this fact to do this definition. Now, let's imagine that we have f of t, the time domain function, multiply it by this exponential, e to the power of minus st. So notice that this function, call it h, which is dependent in these two parts, is really a function of two variables, t and s. Now, if I integrate it over time from 0 to infinity, over t, then you get another function, call it capital F, which will be a function of s. This capital F of s is the Laplace transform of f. So this is the definition. It is a definition that we use. So we're not trying to derive this. It's given to us as is. It's what Laplace, the mathematician, defined. Any questions up to here? Okay. So the definition of Laplace transform, f of x, capital F of x, is the Laplace transform of f small f of t, which is computed using this integral. So we say that capital F is the Laplace transform of small f. We usually use capital letters to denote functions of in the frequency domain and small letters to denote functions in the time domain. This is the notation that we use in this course. So now let's try to find the Laplace transform of the unit step. First of all, I would like to talk to you about the unit step. In control, usually, the examples that we studied, you have a certain reference number that you want to the system to track, okay? So if you do cruise control, then that can be a speed. It can be 120 or 20. Now, that number is really a unit step, can be represented as a unit step. You might ask yourself why we have 1 here as magnitude, but essentially in reality, what you want to do is, let's say, 120 or whatever. The reason we do this is the following. If I go back to the linearity, the properties of linearity, we see that due to the principle of homogeneity, I can always scale my input and it will give me a specific output that is exactly scaled. Using this fact, then what we can do is the following. We can use a unit step always to analyze whatever system that we have. And we have it like a culture, or we have it like a tradition. So for every system that I need to analyze, once I am in the Laplace, once I am in the frequency domain, I can assume a unit step and then analyze its performance and then design a controller. And if that controller behaves very well according to the unit step signal, then if I deploy it in practice, whatever input I will give it, it will also give me a good performance. So this is a standard way of looking at it. It's like in your operations research courses, when you do the standard form for linear programming, you have a standard form that you always work with. You guys took the standard form, right? For linear programs or nonlinear programs. I assume you did. Please let me know if you did or you did not. For those who took an operations research course. So you took
أنا لسه
operations.
قاعد أخلص الآن.
Okay. So for those who took the course, did you see a standard form of any kind? Okay, I take that as you did not. But anyway, so we have a unit step. This is the test signal. So we work with one, but we know because the system is linear, you can always scale it up or down, dependent on your application. And then if it works for a unit step, then you're done. So we just stick to one kind of input as a unit step to represent, let's say, a fixed parameter, desired output. And then with that, we can analyze the system. So it's important to see the Laplace transform of that unit step, because if most of our analysis happens in the frequency domain, then we need to represent the unit step in the frequency domain. So first, let's look at the time domain representation of this function. It is 1 when t is positive, and it is 0 otherwise. Can I make the unit step at 0? Well, then you have 0 input. Yeah, the input to the system is 0. So you have no input to the system at all. Okay. So now we have this unit step. Let me recall the definition of the Laplace transform. What was the definition? The definition was as follows. You have the integral. Let me just erase this. You have the integral from 0 to infinity for f of t e to the power of minus st dt, right? So f of t is just 1, and we're going from 0 to infinity. So it's basically 0 to infinity e to the power minus st dt. That is simply what? Minus 1 over s e to the power of minus s t, and then you evaluate t at infinity and 0. E to the power of minus infinity is 0, so this is 0, minus e to the power of 0 is 1, and then we have minus 1 over s, so it's simply 1 over s. This is capital F of s. So it's the Laplace transform of the unit step. Now, what if I have a non-unit step? Imagine that my input is 100. You will see that due to linearity, it will be 100 over s. Why? Because here I have an integral, then the 100 inside the integral can go out, up to the end of it, you will have 100 over S. That's why we don't really care how far you scale this number, because always you will get something that is appropriate with it. So we use a unit step, and then whatever you want, whatever your input is, you know that it's applicable if you have a good controller that works well with a unit step. And it's a test input signal. So it's really important in this course to know the unit step. Yes, Muhammad.
دكتور معلش ممكن تعيد الاف اوف تي كيف اختفت الخطوة اللي بعدها نسيت.
Okay, what is f of t?
البيس وايز فانكشن اللي فوق.
Okay, what is it equal to?
1 when it's larger. اوكي صح اوكي ممتاز. لان
Yeah.
احنا قاعد نتعامل مع اكبر من صفر فتروح على طول يصير قيمتها 1. تمام.
بالضبط. Yeah. Okay. So now let me erase my derivations. This is the proof. Right? You have 1e to the power of minus st, then you just substitute, and then you get 1 over s. Yes, Faisal.
Doctor, do we always evaluate t from 0 to infinity after the integral?
Yes, according to the definition of the Laplace transform, this is what we do.
Okay, so there is no situation that I will start from 1 or 2 to infinity.
If your function is 0 for a certain range between 0 to infinity, then naturally that part will be skipped, right?
Yes.
All right. So let's take more examples. So then we have a shifted unit step. So what is the function f of t? Can you help me with that? What is it equal to? This goes into your question, Faisal. So what is f of t? Yes, Mazen.
It is 0 from minus infinity up to 2. T
Okay.
less than 2. And it is a when t is greater than 2.
Greater than or equal to, right? All right, so if we do the Laplace transform, you get something f of s a e to the power minus 2s over s. We will prove that. So let's prove it. So what is capital F of s? Again, it's the integral from 0 to infinity f of t e to the power minus st dt. Why is it dt? Because we want to get rid of the time variable, so we integrate and cover all of it. Okay? So once we do that, then you have two parts. You'll have 0 to 2. The function is really 0 up to here. Then it doesn't matter whatever you multiply it with, it's just 0. Then you have the integral from 2 to infinity of a e to the power minus st dt. This is equal to what? I can take a outside the integral. It's just a scalar. Then the integral will be equal to simply minus e minus st over s, where the value of t is from 2 to infinity. This is equal. So when I use infinity, I get 0. When I use 2, we get the following. We get a minus. We have a minus sign here, so it's positive. e power of minus 2s. Notice that we no longer have t as a variable over s, right? Which is exactly this guy. So if you do the Laplace transform and your output or the result has t as a variable, then 100%, maybe million%, be certain that your answer is not correct. So always when you use the Laplace transform, because you're integrating with respect to t, you expect to get rid of t as a variable. And later on, we will see that if you make a time shift of a function, so for the step, really, we did not have this part, e to the power of minus 2s. This part is due to this shift in time. So later on, we will see that there are some tricks and properties that we can use such that you can simplify the function, do the Laplace transform, and use the properties. For example, in this case, if I know the unit step, the unit steps Laplace transform, and then we shift it, then the shifted step is simply just this guy multiplied by e to the power of minus s, wherever that shift you have alpha. And if this is scaled by a, then I know that I need to multiply by a. If I apply these properties to the unit step, which is easier to derive, then you get that function as the Laplace transform. However, you can also get it through the integral. I just wanted to give you an idea that later on, we will have some useful properties that help you actually derive these transform functions. Now let's verify our derivation. Again, we have the integral from 0 to 2, which is 0. Then we have 2 to infinity, and then you just apply that integral. Any questions so far? Okay.
Clear.
Okay. So for slightly more involved functions, you need integration by parts. So this is a refresher. So a function u dv, but if you do integration by parts, it's just uv minus the integral of v du. You pick u such that it is easier to differentiate, and you pick v such that dv it's easier to integrate. So basically the integral of v du is easier than u dv. So if I want to apply this, what happens? If I have t e to the power of minus st dt, I can let u as t, then du is what? It's dt. We can pick dv as e to the power of minus st dt. Then what is v in this case? It is minus 1 over s e to the power of minus st. Okay, now if we use the formula for the integration by parts, so uv is basically t minus 1 over s e to the power minus st. Well, at infinity it is 0, and at 0 it is 0, because if you have e to the power of minus infinity, it is 0, and then if you plug 0 here, it's 0. So this part is gone, minus v du. So I can take the integral 0 to infinity. If I use v here, I have a minus sign here, so that can cancel this minus sign. So it is e to the power of minus st over s. Du is simply dt. This is minus 1 over s square e to the power of minus st. Apply 0 to infinity, and then you get what? You get 1 over s square. Any questions?
كثير دكتور.
Okay. Now, if we again, u is equal to t, dv is this guy, and then du dt, and then you compute v, you just apply the integration by parts, and then you get 1 over s square. Actually, there is another property that we will take later. For example, if you multiply a function by time, then you can, the Laplace transform is simply f, capital F, without that time function, without time component, multiplied by 1 over s. So multiplication by time sometimes is simply, in the frequency domain, is just division by s. But we will look into these aspects later on. Okay, I will ask you to do this on your own. So let's say f of t is just t, and it's a ramp input, and capital F is 1 over s square. Please grab a piece of paper and try to derive it. So again, in addition to the step input, there is what's called the ramp input. That's another kind of input that you want to apply sometimes. Instead of having just a reference signal, you have a varying reference signal, but that variation goes linearly in time. So I want you to grab a piece of paper and find the Laplace transform of this guy, and I will give you the definition of the Laplace transform here. It is 0 to infinity f of t e to the power of minus st dt. It's really important that you guys know how to derive the Laplace transform and inverse Laplace transform, and then use these to design controllers, because this is the essence of this course. After this course, I hope that you're able to do these kind of things and use the frequency domain to make control design. And pretty much everything you will be assessed on in these units and onwards will somewhat relate to that objective, and all of the homework and exams will be also related to that objective. So grab a piece of paper. I'll give you a few minutes to try this out. So I'll set a timer right now for maybe 3 minutes, and if you need more time later, let me know. Any luck? Did it work?
لسه ما خلصت بس قاعد اشتغل عليه.
تمام. Yes, integration by parts, correct. So you got it, Mazen? So yes, it is 1 over s squared. Again, we just solved this, so let me look into it. So basically, this is f of s. It's the integral over t of t e to the power of minus st. Integration by parts with u being equal to t, v being equal to 1 over minus s e to the power of minus st, and accordingly we get an appropriate du and dv. You just apply that, and in the end you get 1 over s squared. So this is the ramp input. It's another kind of input, but it's, let's say, less popular than the step input. Then we have the exponential function, which is e to the power of minus at. Its Laplace transform is basically 1 over s plus a. So again, we will use some properties later on, and we will observe that if you multiply any function by an exponential, then that will constitute a shift in the frequency domain. This is, f of t is simply just a unit step multiplied by e to the power of minus at. The unit step is 1 over s in the frequency domain, so you just add a. So try that too. I'll give you 3 minutes to work on it, and then we'll do it together. Or do you want me to do it on my own? What do you prefer? Let's take a quick poll. We have 18 to vote. Okay, the rest. All right, clearly you want me to do it. Let's do it. So again, using the formula, we have 0 to infinity f of t e to the power of minus st. So we have e to the power of minus at multiplied by e to the power of minus st dt. This is simply 0 to infinity. Oh, sorry, it's actually it's 0 over here to infinity e to the power of minus, I can do this, s plus a t dt, right? So what is that equal to? Tell me. It is minus 1 over s plus a, right? E to the power minus s plus a t. And this is from 0 to infinity. Again, if I substitute infinity, I get 0. Then we have minus minus, it's plus. If I substitute 0, I get just 1 over s plus a. And that's the Laplace transform of the exponential. Any questions about this part?
دكتور الخطوة الثانية أنت وزعت الماينس على الاس والاي بعدين فكيتها عشان تستخدم اللابلاس ترانسفورم.
So, okay, so you mean going from here to here after the first equality?
ايه اتوقع انت حطيت خليت وزعت الاي على الاس والاي عشان تطبق اللابلاس صح؟
Yes, the thing is, so we have, okay, we have multiplication here, right? And this is minus
Right.
t and this is minus st. I want to integrate with respect to t. So in order to do that, first let's multiply these two. And then you sum the exponents. And then you have minus s t minus at. You take t as a common factor. And then you have some constant here multiplied by t. This way it's easier to integrate it, right?
Yes.
Because you're integrating with respect to t. So I just combined them, took a common factor to do this. And it's easier to do it this way for these kind of questions. Okay?
Yeah. Yes, clear. Thank you.
Yeah, no problem. So again, you have e to the power minus at, e to the power minus st. You take t as a common factor and you do this multiplication. And then you have 1 over s plus a. So remember something. Because we have an upper bound here that is actually infinity, this is an improper integral because one of the limits is infinity, which means that sometimes for some functions of time, f of t, this integral will not be well defined, and that will not give you a corresponding Laplace transform. So we need some guarantees or some ways to ensure that a Laplace transform exists before we run into trouble and try to do that integral. So really, the Laplace transform may not converge for some functions. And the other fact is the Laplace transform exists if the integral converges. Because it does not converge, because if f is unbounded, then you don't have a well-defined solution. So it's important to remember that because this integral is improper, we need to ensure that we can actually integrate before we do it. So luckily, there are some guarantees and some conditions that as long as you satisfy them, you know that for a fact that the Laplace transform exists. So a sufficient condition, meaning that if you satisfy it, then you know that there is a Laplace transform. For the existence of a Laplace transform is that if f of t is piecewise continuous, and if it is of what's called exponential order, meaning the magnitude of f, you can find an m as a parameter, L alpha, such that and also you have to find the corresponding capital T. If you can satisfy this condition so that the magnitude of f is less than me to the power of alpha t, where t is greater than or equal to capital T, then you know that there is a Laplace transform. Notice the following. If you cannot satisfy these conditions, it does not mean that Laplace transform does not exist. It just means that we don't know and you have to check. But if you can satisfy these conditions, then the Laplace transform exists. That's why we call it sufficient condition. If we call it necessary and sufficient, mathematically speaking, from a mathematical logic point of view, then you must satisfy this. Otherwise, there is no Laplace transform. But here, if you don't satisfy this, it means maybe there is, maybe there is not. But if you do satisfy it, then you know for sure that there is a Laplace transform. We will clarify each of these items next. But before I do that, I will stop here for questions. No questions or comments or concerns or whatever? Okay. So we say that a function is piecewise. So notice that we're looking into these two conditions and we're defining each one of them now. We say that a function is piecewise continuous on an interval if this interval can be divided into a finite number of subintervals, such that the function is continuous in each subinterval, and also the function approaches a finite limit as t approaches either limits of the interior. So if this part looks like this, where this goes to infinity, then it's not a piecewise continuous function. But because it's here, it's a finite number at the limits of each subinterval, then it is actually a piecewise continuous function. So in every piece, it is continuous. And at every limit, it has a finite value. And the number of subintervals is actually finite. With that, the integral will in no way will go to infinity, because as t approaches infinity, you will have a finite value here, and you have all of these segments being finite and continuous, then you know that the Laplace transform will probably exist. Any questions about this part? Okay. So let's take a quick recap. The Laplace transform is very useful in solving linear differential equation and in analysis and design of control systems, because you transform the equations into a set of easier to deal with kind of equations. It has a certain definition. So basically, if I have a if I have a function of time t, I want to find the corresponding Laplace transform as a complex variable valued function, then we have an integral of f of t, e to the power of minus st, with respect to d with time t. So that integral, if you evaluate it, t will vanish, and you will only have a function of s. The sufficient condition for the existence of Laplace transform is that f being piecewise continuous, and it's also of exponential order. And we will talk about that next. So we call a function f is of exponential order if there exists m alpha t naught such that the magnitude of this function is less than m e to the power of L alpha t for t greater than t naught. So if you cannot find these parameters, it does not mean it's not of exponential order, because maybe you were not able to do it, and there is, let's say, a trick or a way to find them that you were not able to find. But if you can show that they do not exist, you can prove it mathematically, then it's not of exponential order, which means we cannot guarantee the existence of the Laplace transform. But it does not mean it does not exist. It only means that we cannot guarantee it. So it's not, you can try and see and find other ways to show it. So for now, let us try to prove that these functions are of exponential order. So if I have f of t being equal to 1 when t is positive and being 0 when t is negative, then f of t is simply what? It is less than a certain number m e alpha t. I know that f does not exceed 1, so I can simply set alpha to be 0. I can set t naught to be 0. I can choose any value for m greater than 1. If I do that, then I know that this condition holds. And because it holds, then it is of exponential order. I'll stop here for questions about this part.
دكتور انت راح تعطينا ارقام معينه ولا بتخلينا نجرب زي كذا؟
You have to find it on your own. If you can find it, then you call it of exponential order. Here, I just gave you an example. You can pick m to be 100, 1,000, whatever you want to pick it. You can pick alpha to be any positive number such that the me alpha t is greater than 1, which is the actual value of the function.
اوكي.
Yes, Faisal.
Doctor, both sufficient conditions should be satisfied or at least one?
Both.
Okay.
So this is a piecewise continuous function, f of t, right? Because it's 0 before 0, and then it's just 1, a flat line.
Yeah, exactly.
Yeah. Okay, now for the sine function, can you, let's try to do it together. I will not solve it. Just give me some suggestions. Sine of t. Can we find m alpha such that sine of t for any value of t is less than m e to the power of alpha t? You can suggest any numbers. So do you have ideas?
باي
What is by
T.
here?
For sine pi is 0.
Okay, but sine pi over t is pi over 2 is 1, right?
No, I said pi, not pi over 2.
Pi. Okay, yeah, okay, yes. But what I'm saying is, this is just one value for sine. It is 0, but it can be 1. It can be between 0 and 1, dependent on the value of t, right? So we want to ensure that the upper bound works for all values of sine, not only one value of sine. Yes, Mazen.
We can set alpha and t equals to 0 and m to be greater than 1.
Okay, you can set alpha to be 0. You do not set t. So we want this condition to be satisfied for all t greater than t naught. But you can set t naught to be 0. So you cover it for all t greater than t naught. So if m is, what do you want m to be?
Greater than 1.
If m is greater than 1, alpha is 0, then you know for sure that for all values of t, this condition is satisfied. Because you can satisfy it, because you can find the corresponding m and alpha and t naught, then you're good. So what about the third one? We want t to the power of 2 to the power, so f of t is, actually this is 2 to the power of t. 2 to the power of t being less than or equal sum m e to the power of alpha t. So can you find values of m and alpha and t naught such that this is satisfied? Yes, Mazen.
We can say m equals to 1 and alpha equals to 1.
So with that, this is just equal to e to the power of t. And e is 2.7 something, which is greater than 2, so this actually is satisfied. So that is correct. So if we erase that, we can take it. These are the answers. We want some answers. Take m to be greater than 1 for the first one, and you can set alpha and t naught to be 0. And then similarly, you take m and alpha to be 1 for the third one, and set t naught to be 0. So remember, we have a function here, the inequality. This is a function of time. So we want this to hold for all t greater than t naught. So in this case, we just set t naught to be 0, but maybe sometimes you have to even vary that t naught dependent on the example. So if this condition is satisfied and if it's piecewise continuous, then the Laplace transform exists. So with that, I conclude the lecture for today. So we'll talk to you on Wednesday, inshallah. Again, if you have